I'm gonna hit record and okay. So the receiver, we can define some optimality conditions here. And so the received R, this vector of symbols here that we're getting at the receiver, depends statistically on the transmitted vector S sub M through the
Professor?
Yeah.
There we go. Never mind. Just the presentation just started. Sorry to interrupt.
Oh, okay. Yeah. So the previous Zoom session is trying to process the recording, and so it's probably overwhelming my my laptop right now in terms of CPU power. So things might be a little sluggish. So the received R depends statistically on the transmitted vector S sub M through the conditional PDF, which describes the random effects of the channel, right? So this channel has going to impart some effects onto the symbol SMs that are coming across and produces the R that the receiver actually sees. And that's going to be a statistical process that depends to some degree or is conditional upon the actual message being sent, right? So so the question at R is which M are we receiving right now? But M translates directly to the symbol. So really, we're going to estimate we're getting the R. That's a impaired or perturbed version of S. What we really want is M. We know that there's a relationship between SM and M. So this map receiver is the first one we'll look at, and we'll explain what map means here in a moment. So what we want is to look at the probability of getting a correct decision as conditioned upon the received vector R, right? So we want this to be maximized, right? So that's equivalent to saying that because we want to, we're estimating M hat, and if it's correct, that implies that it was M that was actually sent, right? And M hat equals M in that correctness case, right? So the idea of a correct decision is that M hat, the one we estimated, was the one actually sent, right? So now that's a conditional. We can find the marginal by integrating, right? So so then what we're really interested in is the probability of a correct decision. And so if we integrate out the conditional probability while multiplying it or weighting it, as another way that I like to think about it, by the probability density function or PDF of this R and integrating with respect to R, then we can get rid of that marginal dependency and get the marginal, right? So so we sub in this M hat relationship, and now if we step back and think about it, the PDF of R is not really a function of M, right? So that's the, just a probability density function. So really, I should say more precisely that it's always going to be positive. That's so ignore what I said before. But the key point is that the probability density function is always a positive function, right? It ranges from 0 to 1 as a certainty, right? So it's always non-negative, which means that we're multiplying one part of an integrand with a non-negative number. That's not going to affect where this maximization condition occurs, right? So, this integral, remember, is a summation. Now we're just summing all of these positive numbers. So we can kind of ignore this P of R there. And we can interpret this that we will maximize the probability of a correct decision if we maximize this conditional probability in here, right? So what causes that probability to be maximized is what we're interested in. So what we can do is we can search over our M's, our various M's, right? Which is going to be something in that set of 1 to capital M. It's going to be one of those. And so we look at all of those and we perform this calculation and we say we want the one that maximizes this probability, which will in turn maximize that integral and then maximizes the probability. So we don't actually have to go through that whole process unless we want to know what the exact probability is. What we're interested in right now is maximizing it, right? So we like that probability to be 1, but what we're really interested in is let's maximize it. Let's get it as much as possible. So we can just focus on this, narrower focus on figuring out the argument M that maximizes this this integrand, right? And then we know that there's a one-to-one relationship between M and SM. So really we can write this, that we want our choose or estimate the M hat to be the M that maximizes this probability given R. Okay, so now actually we'd prefer to work with the probability of R conditioned upon SM, right? So if we go back here, we have the probability of SM given R. So that means we got to receive something and kind of predict what sent it, right? Whereas this is a little bit more knowable, right? That we can predict the impact on R based upon S sub M. Okay, so if we want to flip the order of these conditional arguments, we use Bayes' theorem or Bayes' rule, right? And that means that, well, we'll continue to look at these vectors as a probability density function, but we have the conditional on top. We have the probability of R on the bottom and the probability of M being sent on the top. Now, that's just applying Bayes' rule to this previous equation here. Okay, so we're just flipping around these the order in which those conditionals appear. Instead of saying M conditioned upon R, we're going to look at R conditioned upon M, or R conditioned upon S sub M. We still want to maximize that because this is an equality, right? We've just gone through this Bayes formula. So now this is where I meant to say that this probability density function R is not a function of M. So it does not affect the argmax process. And so we can ignore it, right? So this is just searching for the M that will maximize this. And so this P of R is not a function of M, and therefore it doesn't matter in this argmax operation. So we can just ignore it. So now we potentially, but really that's our goal, is to directly know P sub M and the effects of the channel on S sub M. We're not going to know that specifically, but we will know it directly in terms of the random process. Still a random process, but we'll know its effects, right? So we can determine the probability of which message is sent, and we can determine the impacts of the channel on SM that produces R, right? So this is more knowable than the previous this previous equation. Okay. All right, so we call this the maximum a posteriori probability receiver. Okay, so maybe we ought to have an oral final exam, and everyone that can pronounce this correctly gets an extra few points, because I had a hard time with it. But it's a Latin term, and it's if we look at from Merriam-Webster, it's talking about inductive reasoning. So it really comes from the philosophy domain, and you may have studied both deductive logic and inductive logic. So inductive is when we're looking at observed facts and trying to come up with a hypothesis that is supported by those observed facts. So we're reasoning backwards from the effect to the cause. Okay, that's inductive. Relating to or derived by reasoning from observed facts. We observe the evidence and induce the symbol sent, considering the prior probabilities of the considered hypothesis. All right. Now, so that's an important concept here. We also have this ML receiver, which is a specialized case of the MAP receiver. Okay, so MAP stands for this maximal a posteriori probability receiver. Okay, but if we look at if each symbol or message is equiprobable a priori, like we know that the probability of which message is being sent is equiprobable, meaning that it follows a uniform distribution. Therefore, its probability is 1 over capital M, where it can take on any of these values from 1 to M, equiprobably, then it is not a function of M, right? That all of these have equal probability. So we can drop that P sub M out of this argmax process. And now it's a little bit simpler. We call this the maximum likelihood receiver. So ML receiver. So it is a subset or specialization of the map. A lot easier sometimes to do this, but you must be aware that it only is optimal or optimal when this condition applies. That the selection of which message is follows a uniform distribution, meaning that your bits, or at least each grouping of k bits, is follows a uniform distribution. So yeah, so both are optimum, but only the latter only under the more restrictive condition. So real quick then, a priori versus a posteriori. I mentioned both of these. So I just stole this from Wikipedia, and you can look it up, but it helps keep these separate. So yeah, as an engineer, you've probably given your friends that are philosophy majors a hard time about their degree, their career. We always like to joke at the expense of the philosophers, right? But much of what we do, whether it's in communications in this case, or in artificial intelligence, machine learning, there's actually a lot of philosophy, surprisingly. So, because we're dealing with a little bit of knowledge here, we're trying to understand what information is being transmitted. So, a priori is knowledge is independent from the current experience. So, it has not a factor of what we're observing. We know it a priori. So, if we know that the message probability a priori is uniform, if we know that beforehand, or know that without having to look at the evidence, then we can choose that maximal likelihood receiver. Okay, so but conversely, posteriori knowledge depends upon our empirical evidence. So we need to observe the outcomes or the effects to determine the cause. All right, so let me real quick look at some of these homeworks and okay. So, are you seeing the homework assignment at this point?
Yes.
Good, good. All right. So, I'll just give you a few hints on some of these, and hopefully you've looked at them. These are really intended to help you master the knowledge, and prepare yourself for the exam, which measures how well you know the knowledge, right? So so I encourage you to work with these and put some effort into them. So random experiment is a very kind of a common toy example that is used where we have different colored balls and we're drawing them from an urn, and in this case they're also numbered, which gives us a little richer set of events that can occur and allows us to look at some conditionals, right? So here, I think what the easiest way of doing this is kind of just looking at these individual events that can occur out of this space. Okay, and so you could draw an R1, an R2, an R3, an R4, or a B1, B2, and B3. So if you kind of go and label those, and now know how many total balls you have, and you know that when you draw a ball, you're going to draw one of those, right? So that's the entire set of events that can occur. And all these other events here, E1 through E5, are more compound type events. And so, here you can write out E1 is going to be what, R2, R4, and B2, right? So that would be the number of balls in that particular event. So what would be the probability of E1 happening on any given draw?
3 out of 7.
I'm sorry?
Is it a 3 out of 7?
Yeah, three out of 7, because there are 3 balls that are in this compound event, and there's 7 total, right? So just kind of work that out on all of these, and so in this case, like E4, E3, that would be the intersection of those 2 events. So write out what's in E4, write out what's in E3, and look at what is in common for those, right? So this one is the one that I realized once I started working on the solution that we talked about the Gaussian random process or random variable, but we did not talk about its related functions, the Q function. And I'm not sure whether you studied that in the past, but we certainly did not review that. So I'll remember to make a note of that in the lecture on Friday. We'll do a brief review of that, and then you should be prepared. And I'll talk a little bit about a hint there, but this one's very relevant to us, right? So we have Gaussian random variable. So this is going to be the noise. It has a mean of 0 and a variance sigma squared equal to 10 to minus 8. So that's going to describe the noise power, right? So, and this is where we need to integrate through a region of the PDF. If the PDF is Gaussian, then the integral of that is going to be this Q function. And so that's where we'll need to do that. Okay, so these are just setting up the different limits of your integrals. So just kind of translate those words into your integration limits. Then consider a communication system. So this is really all about looking at conditional probabilities, right? So and it's an interesting exercise because it's kind of similar to what we just looked at, the difference between a map and an ML receiver. Here, there's a probability of each interference is 0.8, 0.16, or 0.04. These are not the same. So it's a stretch to relate interference to a map or an ML receiver. But if you remember, the ML receiver assumes that all these prior probabilities are equal. Here they're not. So, but we know that they're going to fail when confronted with. So if this receiver is confronted with this interference from A1, it's going to fail with probability of 0, 1. Okay. Most of the time it's going to pass, it's going to succeed, but it's going to fail at this probability. It's going to be a little bit worse with A2. If it gets interfered with A2, it's going to have 10 times more likelihood of failure. And even more so with A3. So basically, you're going to repeat this application of Bayes' formula. You're going to look at these conditional probabilities, set up your equation here, set up your problem, and looking at what is the probability of failure given probability interference. And so you'll see that it's useful to apply Bayes' formula here. This so you're going to repeat this 3 times. Okay. And yes.
So for three, B is the probability of interference, would be.
Well, that's so that's part of setting up the problem is understanding which thing is conditioned upon what other thing, right? So give that a shot here. But yeah, so I think that given that the system has failed, so I think that would be your
B is
B, right? Given, or no, I'm sorry. The probability a system will fail is 0.1, given that you're confronted with a sub 1,
one.
right?
Okay.
And the probability that the system will fail is 0.1, given or conditioned upon A2, right? So work through that. This is more abstract. You got to kind of figure out how to assign these, right? And then this one show that the random process x of t, a cosine omega t, theta, capital theta, where this is uniformly distributed random variable in this range of 0 to 2 pi is a wide-sense stationary process. So go back to the definition. You can calculate the mean and the autocorrelation. And the autocorrelation should not be a function of t explicitly. It should be only a function of the difference in t. But you would have an x of 1t, and x of 2t, and then you'll use some trig identities looking at double angles because you're going to have two of these, right? An autocorrelation takes the same signal but multiplies itself, and then you integrate that, right? So look at that definition, and then finally, is this the last one? Yeah. So hopefully I've drawn these pictures well enough. You've got this distance A here, two different constellations. You can look at the number of symbols here and figure out the number of bits that are used to encode each symbol. From that information, you should be able to calculate the bit rate given the symbol rate. These are symbols, remember, right? Write a gray code for the constellation on the left, right? So that's where, as we go from the nearest neighbor constellation point, only one bit is changing at a time, right? So map this. This is 0, 0, 0, corresponding to bits coming in 0, 0, 0. Write out a gray code for all of these where all these adjacent ones only change by one bit, right? And
does it depend where you start for the gray code, or can you start anywhere?
well,
Start at the most right.
in this case, we're highly symmetrical, so it doesn't matter in this case, right? So, but yeah, if you start here and then go clockwise, let's say, then this one has got to still satisfy the gray code relationship. The last one has to satisfy it with the first one too. Makes it just a little trickier to do. So, but you can either do it brute force, or there's some tricks you can do, that kind of, you can write out a binary truth table here and look at converting from binary to a gray code. It's only 3 bits, so you should be able to get it brute force pretty quickly. So, and then which constellation is more power efficient? So you've got to look at what is the power for each one of these in terms of A, right? So you use a little geometry here, and this one's a little simpler, and this one it's just a little trickier, right? And but write out the vector that corresponds to the power, the distance from the origin for each of these constellations. Add them all up, average it, and look at which one is more power efficient. Okay. All right. I think I'm a minute over, so I'll let you go. Apologize for the sketchiness of the online thing. I'll keep looking for a solution that works, and we'll see you on Friday. So
That's good.
homework will not be due Friday. I'll adjust the due date on it. So okay.
Sounds good. Have a good one.
All right. Take care.